All right, so this is just going to be a simple video on disassembling, um, working with GDB, and well, running, debugging C and disassembling it into assembly, and just kind of looking at that. So if I run and compile this program, nothing happens. And I can go to debugging mode, break it main, disassemble. Run it first, then disassemble, and we see that we have the stack frame, the function prologue right here, which is just setting up the base pointer. Then we have the function epilogue, which pops the base pointer. Then we have 0 stored in EAX, which we don't have anything returned from this main function, but it's kind of assumed that you're returning 0. So this is a return for the value which is stored in EAX. EDI is the arguments, the argc. RSI is the second argument for the function. So the arguments for the function kind of go like, if I look at my notes here, function calls, see that the first 6 arguments for the function would be RDI, RSI, RDX, RCX, R8, and R9 respectively in that order. If I got rid of these, compiled it, went back into GDB again, you can see that we don't get the RDI and RASI values because we don't have any arguments for the function. But we can put that back to the way it was, and we can actually go back to that, disassemble, and we already got to the function epilogue pretty quick here, but we can look at EDI. So if I do a print as a decimal EDI, see we get 1 because we have one command line argument. Actually, by default, it provides the name of the program. So I could actually get what that value is if I take RSI, turn it into a char pointer. Whoops. And then dereference it, print it as a string. And we see that we get the first argument, which is just the absolute value of where the program is located at. Let me try something a little different. I'm going to remove this just to make it a little simpler. I could store some variables instead of a function. And then, I don't know, int pointer c equals value b. Just make sure to return 0 because it's frowned upon if you don't. Also, you should include void in your main because if you don't, void means there's no arguments, and nothing means there's an undefined number of arguments. So let's break it main, run, disassemble again. And we see that we have this fs, which is a segment. I actually looked this up. It's a special segment register. And, this is the offset for that register. It's a special sentinel stack guard value. I don't know. I don't want to look too much into it because I don't know. Don't know too much about it, but I just know that's what that apparently is. All right. So I think the program really starts at like right here. Well, we start assigning values about right there, is what it looks like. So I could do next, disassemble again. So we got the first variable stored, which is right here, which is our 12. I can actually look at that. We see that it's stored as a byte, which is the size, that is the size of an unsigned char. So I can print that off, P dash D. I'd have to chart is an unsigned chart chart pointer. RVP, what is that, minus 0x15. And then I'd have to dereference the pointer to get the value, the decimal value. You see we get 12. I can do the next instruction. And I actually kind of went, so it looks like we already assigned B. So I can actually look at B, which looks like it's right here, which is the value 22. So if I do RBP minus 14, I should get 22. Yep. And we can see that this is minus 15, then 14, and then after that we do a 10. So we go from 15 to 14, we subtract 1 because the size of an unsigned char is 1 byte. And then we go from 14 to 10. If I get 0x. And I believe that's, it says quad word pointer. This is, if this is a quad word pointer, we know quad word is 8 bytes, but this is actually a D word pointer right here. So a D word would be 4 bytes, so we can actually do 14 divided, minus 4 to get to the next point. If that makes any sense at all. I believe that's what's happening. So we can get the value in this pointer if we do... You know what? I didn't cast that as an integer pointer actually, so I really should have done this. But I got the same value regardless. And I can get the value inside of the C pointer. What is that? It's at 10. I do one of these. Whoops. Is it 10? Oh, it didn't store it yet. It didn't do that yet. So I'm jumping the gun. Now I should be able to get the value. Yep, now I can get the value that's at B. So this is actually taking the pointer value that's at C, dereferencing that pointer value, and then getting the value from B. So, yeah. And we can look at function calls. If I make int func, this should be pretty similar to the main function. But I didn't provide any art. There we go. Run, disassemble. And we are not at the function yet. And we see that it already stores the values for the function before it gets called. So, the first variable is an EDI. The next variable is an ESI. First argument. So the first argument is EDI, and the second argument is ESI. Next instruction. And then I'm going to step into this function. We see that there's not much going on because there's nothing in the function. But we do see that it seems to be doing nothing. It tries to assign EDI to, so the first argument in the function to RBP minus 4, but then it doesn't seem to do anything. Okay, this is the char. It's taking it from A. That's interesting. It's taking it from AL. That's not something I thought I would see. And then a no-op, probably because there's nothing happening in the function. We have our function prologue and our function epilogue. But that's interesting that it used AL there. I don't know what that's all about. So, boom. And I can actually look at floating point values right here. So I'm going to do a single precision number, do 10.0. I'm just going to assign it like that, build it, break it main like I've been doing, run, disassemble, and we can see that from the disassembly that XM00 is where the value, the floating point value is stored. If I do a next instruction, now it's stored. If I actually look at, what is it, XMM0, we can see that we have the value 10, but this is actually the binary representation of the number. So with the binary representation, because it's a single precision, we can say that the first bit represents whether it's sign, represents the sign. So if this bit is on, then it's negative. If it's off, it's positive. So we can see that it's a positive number. The next 11 bits are the exponential bits. I think these, I meant to say 8. Yeah, this is 8 digits. And then the next, is it 23 digits are the fraction bits. So that just kind of determines, where the decimal point is. And there's a process to that. And if the exponential bits are above 127, then we know it's positive. If it's below, and the exponential part is positive. If it's below 127, it's negative, from what I understand. So I can actually get, if I take that number, bit shift it to the right by, what is that, 23? And then I'm going to have to do actually 24. Wait, I'm trying to just get the exponential bit. So I actually have to do, what is it? Yeah, that should be the exponential bits. We see it's 130, and that's above 127. So that means the exponential part is positive, which I think means that the decimal point is moving to the left, because that's pretty sure. But it's not, I don't know. I'm not entirely sure. But I just know that this is the binary representation of a floating point. All right. So that's not much, but it's all I got for today. Also, I can do disassemble start. So this is actually where the program starts, even though it's, they say it starts at main. It's a little deceiving. I noticed that there's like a halt, which I kind of looked up. It halts the central processing unit until the next interrupt is fired. So I guess it seems to be that, in Linux at least, it halts the program before it kind of ends the program, which, I don't know, is interesting. And all functions seem to start with this. And I think they kind of implicitly start with that. But yeah, all right, that's all. Hopefully you learned something.